Okay, so this is the code for running the EM algorithm to solve the problem in example 6.1.2. Okay, the problem of Poisson mixture. All right, estimating the parameters in a Poisson mixture. So so basically this is the code, and so what happened was that I added some additional lines there to make sure that when you recycle this, it will give reasonable diagnostics, right? So okay, so it's just a small thing, right? Okay, so just to run this, right? Now, this whole code here, you could actually run the whole thing here. So basically, over here, these are just the starting parameters, okay? And this is the tolerance level of, so basically this is some kind of, when some kind of cutoff, whereby if this cutoff is the difference between the difference between the updated log likelihood is not any bigger than the previous one by this amount, then we will stop updating, right, and report the result. So this is basically for the stopping criteria, okay? So basically the whole thing here, these are your diagnostic plots, all right? Diagnostic plots, which is, so you have to, for different problems, you have to change some of these things, right? These parameters, these variable names, you have to change them, right? You don't have to touch, basically these things you don't have to touch, all right? You just need to change, like for example, over here, right? These are your updating equations, right? So the updating equations will depend on the particular problem. So if you want to recycle this code, you probably have to change like these things, okay? So the form of these things you have to change according to the question. And also somewhere like this one here, this function is, okay, so over here, this will also change, right? Depending on the problem, okay? So the data will also change, okay? So you have to recycle, when you recycle, please don't use the same thing, it won't work. This is only to handle this particular example, okay? Now, let me just run this thing. Just show you the demo, okay? So I've got this thing pasted on my R console, so I run this, okay? All right, so I've completed running it, okay? And if I type Y, okay? So this Y is actually is quite a lot, so I'll just put head of Y, okay? Okay, still a lot, so right. So there are two parts here. The first part is here is the final result, okay? So the final result says that the solution has converged to these values, all right? Alpha equals to this, mu1 equals to this, mu2 equals to that, right? And this is the observed log likelihood and the number of iterations that it took to reach this convergence, right? This second part here, the Y, so this is a list object. So this is a second object, which is actually a table. This one gives you the updating history, right? So this is actually the history of your algorithm updating itself. Now this history is actually important for you to be sure that the algorithm is behaving properly, okay? If you don't have this checker, sometimes if you write a code, your code is not has some bugs inside your code, then you actually get the wrong answer, but you don't know you wouldn't realize it because you have no way to check it. Okay, so recording the history here is important, and we can actually once you have recorded the history, you can actually plot it, right? You can plot the history of the alpha values, the mu1, mu2, and the log likelihood, right? Then we can use this to do a diagnostics, right? So let me show you the plot. So you actually get this plot here, all right? So you can see that the value of alpha has been steadily growing until it reached convergence, okay? But it took a lot of iterations, up to 1,000 iterations to reach convergence. And the more important part here is your observed log likelihood, okay? So it is increasing, right? It keeps on increasing and then stabilize, okay? All right, because we're going to, the whole idea is to maximize the likelihood, okay? So we use this as a way to judge, right, whether the updating is done properly. Okay, so as you can see, the others are also smoothly going towards some value at the end. Okay, so it tells you that this algorithm is actually this implementation is actually done properly. All right. Now, however, let me show you another thing here. Now in the code, right, I said something about let me see. Okay, I gave some comments here. I said try a value of mu1 begin that is larger than mu2 begin, right? So that means you're trying different initial values. Okay, see what happens. All right. Okay, we'll try that. So basically, we just need to. Okay. Right. So here you have this. So instead of 1, 2.5, we swap it, okay? We put 2.5 here, we put 1. And let's see what happens. All right. Now remember here, you see that your estimate currently is alpha is about 0.358, right? Maybe I write this down. Okay. We just. Okay, let me write it down. So your alpha estimate is 0.3589. Mu1 estimate is 1.2544. Okay, maybe 45. Okay. Mu2 hat is 2.6623. Okay. The log likelihood is minus 1989.946. The number of iterations is 1007. Okay. So the starting values, we swap the starting values, right? Now we swap the starting values. Instead of 1 and 2.5, we swap it to 2.5 and 1, okay? So then we run this and see what happens, right? Okay, now You notice here, this has actually changed, yeah? All right, look at this. So for the new one, your parameter estimates has become this. These are just, the other two are just for record. Right? Okay. What do you notice about these two sets of estimates? Remember here, our model is this, yeah? The model is this alpha times I just use I, right? So plus okay. So this is the mixed Poisson. Okay. Now then you look at these two situations here. What do you think? How is this situation related to this probability? Which one is correct, or is it both are correct? What do you think? Any comments? Why do you think when you change the starting values, you get a different result for the parameter estimates? But the likelihood function is equally likely, all right? So what this is saying is that your solution is actually not unique. Your maximum likelihood solution, you have actually two sets of solutions where both are maximum likelihood estimates, okay? Um, but why would you have this kind of situation occurring? Can you get some ideas? Anybody wants to give an opinion here? Right, okay. I think actually the reason is very simple. You look at this form, right? Actually, 1 plus 2 is equal to 2 plus 1, right? And both are equal to 3, correct? So, do you say that this is correct or this is correct? Or both are correct? But clearly both are correct, right? The reason is because when you have a sum here, right? Okay, now this is our data. In our data, we know this, right? Here we have data, okay? Here is our model. Okay, so basically, because both sides, right? If you have some data that is fixed value, let's say 3, it could either be 1 plus 2 or 2 plus 1. So both are okay, right? And precisely it's because of this. You look at this situation here. Now, if you pick this situation, right? Basically, you are, so you pick this, right? Okay. So basically, you have about 0.36 times minus 1.25 something, 1.25 I over this, right? Plus 0.64, the complement, e of minus 2.66, 2.66 I over I, right? Okay, so if you take this set of solution, you produce this, okay? Now, if you take this set of solution, what will happen? So basically, you will get 0.639 is 0.64 times, then this one is mu1, right? So it's 2.6, so E of 2.66 minus, okay, times 2.66 of I over I factorial, plus the complement 0.36 times E of minus 1.26 power I over I, right? It's the same, right? Almost the same lah. Okay, so this part here, the second term is basically the first term here. And the first term here is basically the second term, right? So basically it's a situation of 1 plus 2 and 2 plus 1. Okay, and which solution you use here will actually depend on your definition of population 1, right? And definition of population 2. If you define population 1 to be summer and winter, okay, and we know that old people die more in during winter times, right? If you define your population 1 as the summer death in summer and population 2 as death in winter, then which parameter estimate should you use? The first set or the second set? If you define the population 1 as number of deaths in summertime, population 2, number of deaths in winter, should you use the first set of parameter estimates or the second set? Anyone? No, it cannot be both. I know. Okay, they are both of these solutions are acceptable. But when you when you want to interpret the result, right, you can only pick one of them. Mathematically, they lead to the same log likelihood, but in the context of the problem, right, only one of the set of solutions should be admitted. Which set? you have to refer to the context of the problem. Yeah? So in this case, if you define population 1 as death in summer, population 2 is deaths in winter, you will have to pick the first set of solution, right? Because in the first set of solution, the number of deaths, the mean death is 1.2. Okay, whereas the mean death in population 2 is about twice of that. So this would correspond to your summer deaths, mean deaths, and this would be your winter deaths. Okay, and in fact, this will also be true because less people die in summer. Okay, so this proportion is lower, right? If you pick this one, it is mathematically correct, but it doesn't make sense in the problem. You are saying that actually people die. The old people die more often in summer than in winter. All right, but this is usually not true because it's winter time that people usually fall sick more often, and they also have difficulty accessing medical care because of the weather, right? Summertime is fine. Okay, you can access medical facilities very easily. Okay. And some diseases such as arthritis and all that get very bad during winter. Okay, so what I'm trying to say here is that in your EM algorithm, sometimes depending on what problem you are trying to solve, you may actually, with different starting values, you will get different solutions. Okay, and which solution you need to take up will actually depend on your context. All right, so your context is actually quite important in deciding, okay, among two sets of estimates that have the same likelihood, right? The same likelihood values, okay? If you have two sets of functions where, for example, the log likelihood is one is larger, the other is smaller, then of course you will pick the one that's larger, all right? Okay? Because the other set basically corresponds to what we call a local maximum. All right. So the local maximum, of course, whenever possible, we try to take the global maximum. Okay, not the local ones. All right. Okay. So this part here, I think concludes the part on your EM. Okay. Then after that, after you try out your hand on the tutorial questions, then things will clear up much more. Okay. All right. So now I want to go to the MCMC. So the topic is on Markov chain, Monte Carlo methods. How many of you have taken a Bayesian statistics course before? Have you? Some elective course that focuses purely on Bayesian statistics. Anyone? Okay, if you do Bayesian statistics, you will come across the MCMC because in the Bayesian approach, you actually have to deal with a distribution called posterior distribution. And this distribution, you often want to find the mean of the posterior distribution. Basically, a posterior distribution is just some distribution, all right? Now, you want to find the mean of this distribution, but generally, it cannot be done except in some special cases where you can actually do it by hand. In most of the time, you cannot do it by hand. There's no way you can find the mean of that distribution because by hand, because the density, the probability density function is too complicated. Okay, it's too complicated, so we will have to use Monte Carlo methods to estimate, right? For example, you have some fx which is very complicated. All right, fx is a PDF which is very complicated, and then we want to find this thing. All right. So of course you might think that we can use Monte Carlo methods that we learn, right? So depending on what is this, then we can use all those tricks that we have learned, right? Okay. This is basically just an integral, right? You just think of this as an integral, okay? But then this fx can be very complicated. So those methods that you learn, right, may also not be that easy to implement, okay? Because sometimes this fx, right, it can contain, if you have a formula for that, that's quite fine. Like for example, you may have something like this, whatever, right, some function, okay, doesn't matter. But sometimes, and if you have this kind of form, maybe all those things that you learned previously will be useful, right? You can use that, okay? You can use antithetic variables to reduce the variance and so on and so forth, right? Or importance sampling, things like that. But sometimes your fx can be something like this. There's some function here, and below here there is some integral. And this integral has no closed form. Okay? So when you're faced with this kind of problem, right, it may be very difficult to use your usual way of Monte Carlo methods, okay? So therefore, there's this MCMC method. Actually, it's very elegant, okay? So it solves the problem of. It's also a method to simulate for simulating a distribution, okay? It's the same thing, but the method that it uses involves Markov chain methods. Right, so there's a kind of dependence, okay? There's a kind of dependence between consecutive values simulated, okay? Right, so now I'm going to give you an example. Let's look at an example, okay? Okay, suppose you have a density that looks like this. Right, and you want to find the mean. This is fx. And then find mean of fx, which is basically this thing. Okay. Now, if you use the MCMC method, this is how one particular algorithm called the Metropolis Metropolis Hastings algorithm actually work. So I'm just going to illustrate to you what is happening in that algorithm. All right. So first, you have a starting value. So let's say you start somewhere around here. All right. This is your starting value. All right. So once the starting value is known, you will come up with a proposal density. Okay, this is actually a PDF. So the simplest one is basically a uniform density. For example, you can have a uniform density going here, right? Which is centered on the value that you started, okay? And after that, once you have the proposal density, okay, proposal density with the guess value as the center. Okay. After that, the next step is you draw a proposal candidate value from here. So usually this one people will denote it with Q, what do you call that? Q of X. Okay. So Q of X. So you draw a value from here. Let's say you draw a value, let's say this one. Okay. So you draw a value that's uniform running between in this interval. So let's say you draw this value, right? And once you have drawn that value, what happens is that you compare you evaluate the densities of the target function, okay, at these two values. Okay, the next step is, so this one we call this a target density. Okay. Fx is what we want, right? Then you compare f of so this proposal candidate I denote by y. Yeah? So this is my y, this is my x. Okay. Then compare the density evaluated at y, which is this height here. You compare it against this height. Okay. All right. And then if this is larger than 1 or equals to 1, this is larger or equals to 1 means that the height, right? The height here is like something like you can think of it as some kind of instantaneous probability, right? So if this Fy is higher than Fx, so this ratio will be greater than or equals to 1, right? If this is true, if this is correct, if this is true, accept y, okay? And then your sequence now becomes x, y, okay? Or if this is below 1, what you do is you will draw a uniform 0, 1 random variable. Okay. So let's say this is Fy over Fx is equal to A, where A is less than 1. All right. Then you draw a random variable between 0 and 1, a uniform. Suppose this is your A, right? Okay. If you get a value that's between that's below A, you will accept Y if U is less than or equals to A. Okay. Otherwise, you keep X. All right. So the algorithm is actually very simple. It just does one round that like this. Okay. Every time you will have a proposal. Okay, it will start with a proposal density, and then it will proposal density centered on the current gas, and then it will draw a random value, and then after that, it will do a checker like this. Okay, check if the two densities, the ratio exceeds 1. If exceeds 1, your proposal value is accepted, and then your sequence of simulated value is you add it to the sequence of simulated values. All right. Otherwise, you have to flip. You have to find some draw another random value between 0 and 1 to make a decision. Okay, and that decision will depend on what the value of A is. If your A is very small, then the chance of accepting it will be small, right? And so on. And once you have done this, basically then what happens is, suppose this is accepted. So in the second round, so now you have two, so your sequence of simulated values has actually two candidates now, right? So two guys. So you got two of these guys, okay? And now your Y becomes your X, okay? It's been updated. And then, okay, now your proposal will be centered on the Y value that you accepted previously, right? Because it has been updated to become X. So then you draw a random value, right? So let's say you draw a random value and you hit somewhere around here, for example. Okay. So then, okay, we have already drawn that. All right. So now this is our Y. Okay. So then we compare, right? So we find the height of the target density evaluated at those two positions, right? Now clearly, right, the height of the newly proposed candidate is lower than the original your starting value, right? So in this case, it will fall under this situation. Right, it will fall under this situation. And then you will draw some value and then to decide. Suppose when you draw, right, the value, it fails, okay? So it is larger than A, right? Because if you look at this one, the two ratio, if you take the ratio of this length to this length, it will be actually quite small. Okay, this length is relatively small. Maybe that value ends up at 0.1. So you draw a random number between 0 and 1, you have 90% chance that it will be larger than 0.1, right? So suppose this happens, then this candidate value is not accepted. It is rejected. So we erase, it's rejected, so we erase it. Okay, erase that. And then for the value, we retain it, right? So we add another value here. Okay. And then so on and so forth, right? So we keep on repeating this algorithm many times, right? Maybe suppose 100,000 times or even 1 million times, right? Now, if you do this right, the algorithm guarantees that you will be able to simulate. You will simulate the distribution, okay, and fill it up like this. Okay, this is a very interesting way to simulate complicated densities, all right? And a usual thing is that so this algorithm will generate a sequence of numbers starting from some guess. Maybe then it becomes something like this. Okay, so it's a sequence of numbers, all right? And this sequence of numbers is supposed to represent this distribution. But there's actually a dependence between the numbers here, all right? This dependence is because when you want to move the algorithm, right, where your proposal density actually can start, it's dependent on the previous value, right? So that's why there's a Markov chain here, because there's some kind of dependence that goes on in this algorithm, okay? The thing is, when you have this sequence, right, those that are, so you have, maybe suppose you generated the sequence like this, okay? Okay, so a sequence is, this is value 1, this is, okay. Now, the sequences that the values that you generated at the beginning, right? These have actually strong dependence. So the dependence will actually weaken. So let me see. So maybe up to this point, they are not IID from fx, okay? But starting from some point after, so whatever you see here will be IID from fx, okay? The simulation actually will converge to some kind of stationary distribution if you iterate it long enough. So because of that, there is actually a term called burn-in. Okay, burn-in. So burn-in is you actually discard, all right? It is saying something about the values that are, so if your burn-in is something like 1,000, okay, suppose your burn-in is 1,000, that means you actually throw away, okay, the values that you simulated at the beginning, right? You throw that away because these are not IID. So if you mix them together, it will disturb the properties of the simulated distribution, right? So what happens is that taking into account that the sequence of values generated at the beginning are not IID, so we will actually discard maybe the first 1,000, 2,000 or whatever, okay, and then only use the remainder as to construct the simulated target density, right? And of course, the question is how much to throw out, right? Burn in. Generally, there's no magic number, right? I know everybody wants a magic number because no need to think, right? Magic numbers, you can just quote that number and then say that somebody said that, right? But really, there's actually no magic number for burn-in. You might actually discard like the first 10% of your values, okay, or even 20% or 30%. Doesn't really matter. In fact, the more you discard, the safer it is, right? Okay, the remainder that you use will be almost sure to be IID. But the problem is that when you simulate values, right, it takes up computer time, right? So if you discard too much data, then basically you're wasting computing time, okay? So this part here has to be some kind of balancing act, right? You don't discard too many, because if you discard too many, then your computer might have to run much longer to actually simulate the values that you want, okay? But if you discard too little, then the quality of your simulated values is not good, all right? So generally this, how much to discard, generally this is maybe dependent on the particular problem, right? Okay, so this is the general idea about Markov chain Monte Carlo. It's pretty easy to appreciate. Let me show you the lecture notes a bit. Okay, so this is the right. So this is the short introduction. So you can read about this. Okay. So basically, this is an example verbal description of the method, right? So you can go through this, and I just gave you an explanation, right? Which is basically that. Now this part here is the formally, this is the algorithm, the way we write it out, right? But over here, you don't have to worry about this term here, the ratio of the two proposal, conditional proposal densities, because over here, there's actually a result here. Two kinds of proposal distribution, symmetric and asymmetric. If we use the symmetric proposal distribution, like for example, uniform or normal, we can actually use proposal density that's normal. If you have symmetric proposal distributions, your Q condition on Y, okay, your conditional distributions, they are the same. Okay, when they are the same, then over here, this part will just become 1. And your decision rule here becomes checking this one, right? Basically, this one minimum of pi y over pi x, comma 1. Basically, this is like is taking whichever that is smaller. If pi y over pi x is larger than 1, this will be equal to 1, right? Okay. So if this is the case, then it will just accept the proposal, right? And as you can see here, right, if this is equal to 1, accept the proposal, and then you add it to the sequence of accept simulated numbers, right? Otherwise, you will generate a uniform random variable u and then check, right? Check whether u is below this part here, right? Because if otherwise, that means this one is smaller. So you check whether u is less than or equals to this, okay? And you will accept, if this condition is true, you will accept, and then you will set include the proposal value in the simulated chain. Otherwise, you will retain the previous value, okay? And then you basically just repeat the steps, right? So the algorithm is actually very simple, involving iterative generation of a proposal value from some proposal distribution, and then do a checker like this, okay? And over here, this is an implementation, right? So basically, you also don't need to, so you can actually recycle this code, right? Depending on what is the target density that you want, okay? So you need to specify the form here. So this is actually a normal mixture, right? So normal mixture, which is this part is a normal density, right? 0, 1. It has a 1/3 contribution. plus this part here is a normal density with mean 2 and variance 1, right? And the contribution is 2/3. You can check that this is actually a probability density function, okay? And please check this on your own, yeah? See that you can confirm that this is true, okay? And this is actually very easy to check. For example, let me see. Let me clear this. Right. So your pi x is 1/3 times this. Okay. So you want the mean of x, right? So this is basically integral pi x. Okay. All right. So as you can see here, this is easy to evaluate because this part here, hello, hello, yeah, I think yeah, I think okay. So so this one is the mean, right? So this is the PDF of 0, 1 normal. So this is the mean, right, of a 0, 1. So therefore this is 0, right? So over here, this is also the same, right? So this is the density of a normal with this n2, 1, right? So here this is the mean, right? So this becomes 2, okay? So you have 1/3 plus 4/3. So this is equal to 5 over so this one is that's 2, right? Okay. Okay. So it's 5 over. Sorry, this is 0. Okay. It's 4/3. All right. So the other part I leave it to you. Okay, to verify that the variance is 17/9. So basically, you just need to find this, right? So this is basically so on, right? 2/3. Okay, so this one you can use the property of the normal distribution to help you find. All right. Okay, it's actually very simple to do. Okay, so I leave it to you to verify. All right. Okay. Now, so when you want to recycle this code, let me go back to. Okay. So basically, you just need to change the target density, right? Depending on what that thing is. And over here, there's nothing that you need to change here, right? There's nothing that you need to change here. So over here, you look at this one. This one, the proposal density, I'm using the normal proposal density instead of the uniform. Okay, it's okay. You see that when I use the proposal density, right, it is centered on the current value. Okay, and here I choose a proposal density that has a standard deviation of 1. All right. So this should be sufficient. Yeah, your proposal density you can use uniform or the normal. Okay. And therefore, this part is basically coding the algorithm. It's very simple. And so from here, this part, you are basically creating the Markov chain here, whereby you notice that the next value that you use in the algorithm, right, depends on the previous value, okay? So that's why you see here Metropolis, right? Over here, it is giving the value that is the previous value, okay, in your simulated sequence, all right? Okay, so after you've simulated, this is I've simulated 500,000 values. So for the burn-in, I discard the first 10%, all right? So this part is just to do verification, all right? So this part is to check the mean and variance of the remainder after you have discarded, right? Okay, so you look at the result here. Okay, so if you simulate it properly, it should fit very well. Okay, and so this is one illustration. Okay, you can read this. Now I show you two examples. Show an example whereby now your proposal density, right? There's a variance that you can specify. Okay, you can specify the variance of your proposal. Like for example, your uniform, you can make it run over a long interval or a short interval. Okay, so the variance, you can control the variance of your proposal density. Now then the question is, how should you tune the variance of your proposal density? What happens if it is too small or if it is too big? Okay, so I'll show you the consequences of setting a variance that is too small for a proposal and too high. Now, if you set the variance to be too small, right? You see that the simulated values are all not correct. Okay, you will not be able to simulate the target density, so it will break. Okay, you will get some wrong distribution. If you simulate, so it's very bad if your standard deviation is small for your proposal. Now, if you, on the other hand, if you set it too big, you will find that certain parts are very, well, this is not too bad, but it's not that good either, right? You see that there are notable gaps around here, okay? So for normal mixture, if you read the normal mixture over here, if you're simulating for normal mixture, the variance of the proposal density should be about twice of the variance of your target density. Okay, so if you pick that value, then that means you will not need to simulate so many values, right? For example, if people need to simulate 1 million times using some suboptimal variance, okay, of the proposal density, then if you use the optimal value for the variance, you maybe need to just simulate 100,000, all right, rather than 1 million. Okay, so So of course, both of them will work, right? It's just that one of them actually requires less. You don't have to simulate so many values in order to get to the density that you want. Okay. So so that is for normal mixtures, right? As long as well, it doesn't mean that you have to specify exactly equal to this value. Okay. Any value that is close to it will usually work. All right. So even if you don't put the variance of the um, proposal density to be 3.7 in this case, it will still work. All right. It's just that if you put it too small or too large relative to 3.7, then you're going to run into problems. Okay. So this is to give you some background on theory. All right. Okay. So now I will show you a simulation of the what is going on in how does it eventually build up that the distribution, right, using MCMC. So I'm going to run this code that I have. Okay. Let's see. Just a minute. Okay. Right. Okay. So let me just run this thing. Okay. So look at this simulator now. Let me start my. So let me just run the simulation. Okay. So here you can see that this is so this value is my starting value, right? 1. Okay. So then this is my proposal density, right? So this is a density that is having a width of 10 units, right? So the height here is 0.1. Okay. So this is a uniform density. Okay. And within this interval, I randomly sample a value, right? So let's say I got somewhere here. So then I have this line here, all right? Okay. And then I compare the two values here, right? The R value, okay, which is the density of this, the density evaluated at this value, which is 4.6 something, divide by this value, okay? So I get the ratio 2.322, which is larger than 1. So I will accept this value as a candidate, okay? All right. So let me run. And so this is another simulation. Now this time, okay, let me restart this. Okay. So in this case, you also have the acceptance. This one also acceptance, right? This one also acceptance because the ratio is more than 1. Okay, so this is 0.99, right? So it's also accepted, it's very close. Okay, so this one also accepted. Okay, so when you have the ratio below 1, right? So this is 0.98. So there's actually a 98% chance that you will actually be accepted, right? And it got accepted. Okay, so we look at some more examples. Okay, now look at this one. In this case, the proposal here is actually not accepted, all right? Okay, apparently although there's an 89% chance of accepting it, but when we drew the uniform random variable, in this case, it happened to be something larger than 0.989. So it got rejected, and therefore it got stacked together. So the value is remained, right? So I have got two values that are the same stacked together, okay? So now let me try to run this. Let me try to run this think in a simulation, all right? So one after the other, yeah. Okay, so I'm running a simulation now. You can see that this is the process of generating the values, right? So if you want to, you can actually this code is not very hard to write. You can keep on it as long as you have some ideas about how to go about it. Then you can just loop it, and then you can have this kind of animation running uh, in R. Okay. Now you can see that the values are starting to accumulate in the regions where you have the highest densities, right? It is accumulating, right? Okay, the values there. So I've set it to run 1,000 times, so we can see the how the values are simulated and how slowly they become more and more like the target density. Okay. Okay, so I think you roughly get the idea, right? You can see, of course, it will take much longer time to run before you start to see them piling up, right? But I think you get the idea, right? You can basically see how by iterating this algorithm repeatedly, you are going to get the target distribution that you want. Okay. All right, okay, so I think I will stop the animation. Okay, now. Okay, so let's go back to. Okay, so again, you could actually start at anywhere, right? Okay. Okay, so start at -5. I think I had a small bug in the program where I kept plotting this dot. Okay. Anyway, you could start at here. So for example, if you start at here, it is almost sure that because this height is very low, right? So any proposal that you get, as long as it's going to the right hand side, I think it will accept. All right. Okay. Like in this case, surely accept, right? So you move here. Okay. Now the point is this: if you have, so this is the variance of your proposal, right? If it is too short, right, what will happen? Okay, let's go to the drawing board. So if you have just now, right, it's something like this, okay? If you, so this is your proposal density. So this is proposal density. What happens if your proposal density is very short like this? Okay, or something like very long like this. Okay, let's look at the short one first. If it is this short, right, what is its effect on the simulated values? So if it's this short, right, you basically every round, right, you could only move this. There's only this way of moving, isn't it? Okay, and so therefore it is very. If it is this thing is very short, it might be very difficult for you to actually propose values that are at these edges. Okay, because it's too short. Every time it moves, right, it's moving very. It's just moving around some neighborhood like this, right? So certain these neighborhoods will become overrepresented, whereas these neighborhoods will become underrepresented. All right. So that's why when it's not surprising to see this particular pattern. You see here, right? In this case, this one is overrepresented, right? Certain parts are overrepresented and a lot of parts are underrepresented. Okay. If you move too wide, okay. Now, if you move too wide, if your proposal is running something like this, very wide, right? The thing is, okay, you will not have problem covering the entire target density, but you're probably, because there are so many possibilities here, right? So for example, if you are centered around here, okay, you move from here to here, right? So this is your density, right? The height is your pi x. Now, if it is covering too wide, right? So you have some parts where the pi y will be, so if you come here, it will be accepted. But then you come here, it will be rejected, right? So because this is shorter than this one. And similarly here, right? So in this case, you will find that it is very difficult to, it is very difficult to home in on some region of your density where there's a lot of mass. Okay, like for example, this part here, right? There's a lot of mass, right? But if you use a too wide variance here, this part here you may not be able to build up to this density, right? It may, because it's simply every time you are here, it will just move away. Okay. So the best one seems to be try try to estimate the variance of your target if possible. Okay, target density, and then take something like twice of this value. Okay, this should usually work, right? Okay. So I've given you the script to reproduce this figure, right? The script to reproduce this figure in Spectrum. Okay, please run it. Yeah, run it and play with it to get some ideas. Okay, if you are creative, you can also change these things, right? You can change your target density. You can change it to the T distribution or some other distribution that you are interested in. And then you can basically keep this part and then you run it and see whether you can actually obtain a simulation. All right, so you basically don't have to change this part except this part, right? When you fit the target density, of course, it has to be something that you are interested in, right? Okay, so here you can change it to something else that you are interested in, okay, to see what it looks like. So this one, I leave it to you to play around, okay? All right, okay, so I think it's almost 4 now, so I think that's all I want to talk about for MCMC for today. All right. So are there any queries from you? So this part is actually quite brief, and the algorithm is also quite simple to execute. So this is all we are going to talk about for MCMC for this course for this time. Okay, any queries from you? All right. Okay. So you can always ask later, right? Next week. Okay. If when you go through this again, you have some queries, you can ask again. All right. Okay. So that will be all for today. And for those of you who haven't submitted your assignment 3, you have 1 more hour to do that. All right. Okay. So thank you for listening. I'll be stopping the recording now.